Good afternoon, everybody. Let's give the team another minute or so to join this session about hydraulic tank optimization and coolant filtration. So let's start. So again, first of all, welcome. Thank you for joining this breakout session about hydraulic tank optimization. And the part two will be focused on coolant filtration. The presentation will take about 20 minutes and will be a question and answering session at the end. So as I said, feel free to raise questions at the chat function. Quick introduction about myself. My name is Sietse Bars, and I'm the Market Development Manager for the Hydraulic and Industrial Process Filtration Division. Having a mechanical engineering background and working in filtration since 2007, with expertise in hydraulic filtration and off-highway mobile markets. In my current position, I'm supporting our large OEMs with their current, but especially their future challenges. So the agenda of the first part will be by answering the question, why optimization of the hydraulic tank? I show you some return on investments. So this is not only nice words, but also, let's say, numbers that counts. I'll explain the program, the tank optimization program, backed up with a case study and an overview with some available resources. I will do this fairly quickly. We only have roughly 10 minutes for this first part. It normally takes half an hour. So I will go very quickly over the slides. But again, feel free to reach out to me or to my colleagues if you have further questions after the session. So let's answer this question first. So why should we optimize hydraulic tank design? Well, hopefully after answering this question, you have a better understanding about the impact of the hydraulic tank to the total system. So over the recent years, environmental concerns have led to pollution reduction legislations and a growth in electrification of mobile machinery. At the same time, rising cost pressure are driving OEMs to seek design solutions that maximize performance and minimize the total cost of ownership. And focusing on the hydraulic tank optimization can offer many benefits to help solving these challenges. We are not only reducing the tank size, we're reducing the tank size, but also in the same time, we're improving the performance by optimizing fluid duration. We can improve the temperature dissipation via the tank, but we're also definitely focusing on the commercial and environmental benefits because those are equally important. So when we look at the basics about tank optimization, we focus on three key aspects: air contamination reduction, heat dissipation improvement, and flow improvement. So when we zoom in a bit more on the air contamination, if you reduce the amount of air contamination, you can actually improve the machine controllability. Air is having oxygen, so therefore it starts the corrosion aspect. And also air bubbles are causing similar kind of cavitation symptoms in the pump. So all kind of things you would like to avoid. So by reducing the air contamination, you're improving the safety, but also improving the component lifetime. And therefore, safety is going up, and repair and maintenance costs are reduced. Heat dissipation have a direct impact on the oil properties and the oil lifetime. While the oil is a very important component of the hydraulic system, so we need to make sure that the oil properties remain as is. That can be done, of course, with the proper thermal management, including heat dissipation via the tank. This will improve the component lifetime and therefore will reduce the repair and maintenance costs. But the most important aspect of tank optimization is controlling and improving the flow distribution throughout the tank. By improving the flow distribution, we can utilize the full tank volume. And that's basically what we call tank optimization. And that will establish us to reduce your tank size. As said, the tank size reduction is the most important aspect for the tank optimization because it will lead to multiple benefits. First of all, for example, weight reduction. We can reduce the weight of the tank by making it smaller, less fluid, therefore reducing the weight. And with a traditional combustion engine, it will reduce the fuel consumption and CO2 emissions. And of course, it will reduce the operating costs. Weight reduction can also establish that the payload can be increased. So multiple advantages by reducing the weight of the hydraulic tank. The tank size reduction also will establish a reduction in waste, environmental waste. We need to protect, of course, our environment. We need to protect our globe. So carbon footprint is really important, and we need to minimize the environmental impact. So not only from environmental aspect, but it also go from an operational cost because this hydraulic oil needs to be disposed, and this comes at a cost. And last but not least, by tank size reduction initiatives, we can reduce the machine footprint. And especially for these first and second generation battery electric machines, space is limited, footprint is limited. So if we can reduce the size of the tank, that means that space is freed up for other components, like installation of batteries, for example. And that on itself will help you to improve your machine efficiency. So a couple of numbers, and now I need to step up my pace because we're running out of time quickly. These are a couple of numbers on a mid-size wheel loader, where based on the tank optimization, we have been able to reduce the tank by 75 liters. We have been able to reduce the weight of this hydraulic tank by 100 kilograms. And when we're looking at the manufacturing costs, it's quite important for OEMs. We have been able to reduce those costs by 1 million euros per machine series per year, mainly because of reduction in hydraulic oil. But almost equally important, or maybe even more important these days, is the reduction on the environmental impact. In this particular case, we have been able to reduce the amount of oil that needs to be disposed by 500,000 liters per machine series per year. So significant savings can be established by tank optimization without jeopardizing performance. So this is really a win-win situation. So let's talk about the program to bring these tank innovations to the markets quicker. So we have decades of experience, and our engineers are more than happy to support your engineering team with the tank design and optimization of the tank design. So the program is actually built out of three pillars. Actually, the first pillar is the consultation. So my apologies. So our engineers are getting in contact with your engineers to establish, let's say, the key objectives. Are we really focusing about minimizing the tank design, the footprint, or are we trying to maximize performance, or a combination? Based on those interviews, we will start the simulations. We start the simulation with the jump-off point, so the current situation. Then we do a couple of iterations on the tank design, rerun the simulations until the performance is where it needs to be. Then we start almost like freezing the design. But before we freeze the design, a prototype tank typically has been built, and we can test the performance of that hydraulic tank in our laboratory in Urjala, Finland. And then, of course, we try to match and test if the results from the laboratory tests are equally to the simulation results. If those results are matching, and that's quite common, we can take it to the last step, and that's on-site testing, where you can actually test the performance of the hydraulic tank on a working application. And then after step 3, the design of the tank can be frozen, and then the machine can be taken to series production. So the next couple of slides will show you a case study. This is based on a case study for a forestry machine. On the left-hand side, you can see the current tank design. On the right-hand side, you see the future tank design. So from a first impression, it looks very similar, only it's much smaller. This tank was reduced roughly by 20% from all angles. And we see a couple of changes that improves the performance of the tank. So first, we have relocated the suction ports. So let me pick a pointer. So we relocated the suction lines from the back side of the tank to the front side of the tank. So there's more space between the filter and the suction lines, because there's one critical aspect to maximize the path from the returning oil to the suctions. Another thing that we have done is that we've created a so-called internal baffle plate. And this baffle plate allows us to control the flow distribution. Again, to optimize the flow distribution throughout the tank. And again, this will increase the path from the returning oil into the tank towards the suctions. And the most important change is the change of the return filter. So we changed from a standard tank mount return filter that typically is having auto infiltration with a vertical release of the fluid into the tank, into a tank mount return filter with our unique into-out filtration. This tank mount return filter is the Parker GLF filter, And with this inter-output filter, we can establish a much lower flow velocity. That means the speed of the oil that is released into the tank is much lower compared to a conventional tank mount return filter. In the beginning, I said, to maximize the path is basically one of the important things to optimize the tank performance. And the second important thing is to reduce the flow velocity. And with our GLF filter, we can reduce the flow velocity, and we can even control, let's say, the release of the oil into the tank. And this particular situation, we've chosen a perforated funnel over 270 degrees for a horizontal release of the fluid inside the tank to give us the optimized results. This is difficult to see, but the tank has been reduced roughly by 20% from all directions. And here on this image, you can see the flow distributions. We call this the oil flow streamlines. And on the current tank design, you can see on the backside, basically a passive zone. So the oil is not moving in this side of the tank. In the future tank, you see that the full volume is utilized, and therefore, let's say we are maximizing, let's say, that volume of the tank, that footprint. You can also see the flow streamline velocity, so the speed of the oil. That tells basically red means high flow speeds, dark blue means very low flow speeds. That's basically what we try to establish. I have a quick animation that I will show you as well. And I will pause it here. So here you can clearly see that the oil is released in the tank in a vertical way at a very high speed. Because the suction ports are also in the same, let's say, area of the tank, that basically means that the majority of the fluid is straightly passed on from the filter to the bottom of the tank and goes into the suction lines. If we compare that with the future tank design, it's a total different story, where you can also see that the flow velocity is much lower. Oh, my apologies. So here you can clearly see that the flow velocity of the oil that is released into the tank is much lower compared to the current tank situation. Again, that's improving the deaeration and minimize air contaminations going into the suctions. Here you can visually see, let's say, the air volume fraction. So the amount of air that goes into the suction versus the amount of oil. Dark blue means that only oils are going to the suctions, and red basically means air. Of course, on the top you can see air because that's linked to atmosphere, so that's not a problem. But on the current tank situation, you can clearly see that on the position of where the suctions are located, you see this greenish color, meaning still lots of trace of air are there. So that means that air is sucked into the hydraulic system. In the future tank, you can see only this dark blue color, meaning that almost no air is entering the suction side. So all the air that's going into the tank will be deaerated through atmosphere. Some results, and again, we need to do this fairly quickly because time is running out. Tank footprint reduction, 21%. Oil volume reduction, 24%. Overall weight reduction, 19%. Air contamination reduction, 76%. So significant saving on deaeration. We have reduced the flow velocity by 50%. And we see, let's say that we've minimized the amount of passive zones and therefore utilizing the full tank volume. So from a performance point of view, all kind of advantages that really benefits, let's say, not only you, but also your customers. But this is performance. If you focus on the commercial aspect, with the new tank design, with the current quantities of 5,000 pieces per annum, we have been able to establish a cost saving for our OEM approximately €1 million on the annual basis for this machine series, mainly caused by a reduction of hydraulic oil. And instead, we're focusing on the technical performance, we're focusing on the commercial performance, but the environmental performance is these days equally important. And with the future tank design, we are actually saving 1.8 million liters of hydraulic oil that doesn't need to be disposed with this new tank design. So again, significant savings on the liters of oil, on the costings, but also on the performance side. So resources, so we have a dedicated landing page on parker.com. Feel free to watch that landing page with a brochure, with the case studies, with white papers, with interviews, with videos. And before we continue with the next session, I would like to show you a 3-minute success story that we've done together with Sandvik.
Sandvik Mining and Rock Technology is a world-leading manufacturer of underground drills, loaders, and dump trucks. I'm Jussi Suomi. I'm a hydraulic engineer for Sandvik Mining and Rock Technology, Load and Haul. We contacted Parker to help us with the tank design so we could optimize the tank layout and reduce the size in this battery loader and improve the aeration in the tank. Parker tank optimization program includes simulation, lab testing, and on-site testing in the machine. It calculates and measures the ability of the tank to deaerate the oil coming in. Selected tank and selected filters from Parker are internally and externally customized for just this machine to optimize the serviceability, the small footprint in the machine, and the deaeration of the oil. The patent-protected Parker filters allows us to make sure that the filtration in the machine is always correct and on level it should be, and this allows us longer service life of the machine. New tank design and positioning of the filters allows us ground level maintenance and service safety, reducing the cost of service. Reduced oil volume of the tank is a huge benefit, especially in a battery machine where you have tight spaces. Smaller oil volume and environmental impact. Improved deaeration extends the component lifetime. With these great results, we will contact Parker for future projects for simulation and testing of the tank.
All right, so let's go back to the presentation. Back to the second part of this presentation. Again, time is very limited, so we'll cover this topic fairly quickly. This is about coolant filtration. So at the moment, we are developing a new coolant filter specifically for battery electric and hydrogen fuel cell powered machines. I'll explain you the filter concept, the field testing program that's ongoing, and also some preliminary results about the contamination and conductivity findings. So we're developing a new GCF coolant filter specifically for these new high sophisticated cooling systems who are really needed, let's say, for the next generation battery electric machines. Cooling systems need to be protected, and therefore Parker's recommendation of to install a particle coolant filter. So why the installation of a coolant filter? Well, contamination is in every system, so also in the coolant system. This can be built-in contamination on the hoses or on the cooler, for example. So this needs to be removed. Potentially, sometimes rubber compounds using peroxide will start crystallization, and these fibers also entering the system and flush into the system. Contamination that enters the system via the air breathers. Typically, there's an air breather on top of the expansion vessel, so potentially contamination can enter the system via there. Wear and tear. There are not a lot of moving parts, but still you still have the water pump, electric and galvanic corrosion, oxidation. So all kind of aspects that we need to consider, and therefore we strongly recommend the installation of a coolant filter. And the coolant filter will also help to reduce and control the conductivity. System specifications. Obviously, let's say we have adjusted our filters to be compatible with coolant liquids. So we've selected the right materials, the right adhesive, the right seals to be successful. We have just established a special bypass setting to guarantee the maximum allowable differential pressure at all conditions, because the pressure of these systems are maximum 2 bars roughly, somewhere between 1 and 2 bars. So the differential pressure over the filter needs to be extremely low. And we have multiple filter size and port sizes to cover your needs. A couple of features were important. I said the filter is there to protect the coolant components by removing harmful contaminants, but to some degree it also helps to reduce the conductivity. The filter is developed so to allow, let's say, lowest possible differential pressure, So typically we try to aim for 0.05 bar differential pressure, but that in combination with a very high dildo capacity and with environmental friendly element design. The filter element remains inside the filter bowl to optimize also the system designs. And it's a heavy duty, robust design, especially, let's say, needed for, let's say, off-highway mobile equipment. This filter is patent protected. It's having two main advantages. It guarantees the aftermarket retention. So that means that your customers need to go back to your distribution partners for genuine spare parts. But also equally important is it guarantees the quality of filtration, because you don't want to jeopardize the quality of filtration for these high sophisticated, highly costly machines. So we're running some field testing at the moment with multiple customers, but we also do internal field testing with our colleagues at the Caddy division. And we're testing, let's say, multiple options of the coolant filter to determine the correct filtration media. What we're doing, we test the conductivity impact on the filter. So before the filter and after the filter, we're monitoring the coolant cleanliness, and we also examine the elements who are returned from the field about what kind of contaminants are trapped in our filter elements. So that's ongoing at the moment. So quite important, some preliminary findings, and my apologies, I'm going really quickly. This is an example of a cooler that we have studied. So we ordered a standard cooler, and we flushed the coolers to remove all the internal contaminants. And we have did an examination of those contaminations. On the right-hand side, you see a couple of images, and there you see really a high amount of big metal parts, but not only metal parts, also large fibers. But on the graph on the left, you can actually see that the biggest quantity of contamination are the really small particles, actually between 5 and 15 micron. So in that situation, you actually cannot see those contaminants. So if you have a 150 or 200 micron, let's say, filter installed on your coolant side, that rough filter efficiency will definitely not capture those small particles. So therefore, we also recommend a much finer filtration efficiency, also to remove those harmful smaller contaminants. On this screen, you can see, let's say, an element investigation that we received back from one of our customers. This coolant filter was installed on a battery electric mining machine. You actually, you can actually see on the images the high amount of contaminants, especially also the larger size contaminants. So the contamination actually on top of the filtration media. So again, this confirms that contamination is definitely entering the coolant system as well. Not only big particles, also small particles, and those particles simply need to be removed. Otherwise, the water pump or other components will fail. And also those particles, especially metal particles, do affect the conductivity. So conductivity will go up. That needs to be reduced, especially for fuel cell electric machines. Preliminary results on the conductivity. Our filter was installed on this machine between hour 40 and 147. And that tells you also by removing contamination, you can reduce conductivity. Conductivity is not always equally important, but as said, especially on the battery side and on the hydrogen fuel cell powered machines, conductivity is a really critical indicator and needs to be controlled. And our filter will definitely help with that. And then another finding about, let's say, contamination entering the system from the outside. In this image, you can see the quantity of silica, SE, is increasing from 0.9 to 4.3 milligrams per kilogram. That actually confirms that sand in this situation is entering the system from the outside. And therefore, again, a quality filter is needed to make sure that those contaminants will be captured by the filter and don't cause any problems with the cooling system. So that was my presentation about hydraulic filtration, optimizing the tank, and the new coolant filter that we're developing at the moment. So I'm looking at the questions. I see a question from Adika. Above which sizes is meaningful to investigate the oil tank optimization? Well, there's not a real, let's say, one answer to that question. We've done it for very big rigid trucks, let's say 100-ton rigid haulers, but we've also done that for really small 4x4, let's say, military vehicles. So I would say from 50 liters to 5,000 liters, all those tanks can be optimized. What we do see is where footprint is important. Typically, it's having the most advantages. Typically off-highway mobile equipment, but also renewable energy, wind turbines. Footprint is really limited in a wind turbine, so there also tank optimization is really benefit. So do you also have coolant filters for closed circuits? Yes, actually the cooling system is almost like a closed circuit, but you always have this some sort of a breather function to atmosphere, because you need some sort of like a pressure vessel to control the, let's say, temperatures. So our coolant filter is also suitable for those closed circuits. Then I would like to thank you for your interest. Thank you and have a great day.